The goal of this video is to give a tutorial discussion of how we approach this problem. And so our problem here is that we have a galvanic cell provided to us with specific amounts of different ions or substances. So we have an iron side and we have a lead side. We have solid lead, lead ions. We have solid iron, iron ions. And then we also have potassium nitrate present in those solutions. And our goal here is to identify what's our cell potential and how do we identify our cell potential using our Nernst equation and our activities present here. So let's look at our problem here. So we have this information provided about these different cells. So we know that one of them includes lead nitrate and also potassium nitrate. So if we would see then our other electrode includes iron ions and then potassium nitrate as well. So we have these solutions present. And when we're looking at identifying whether all of these solutes are completely dissolved, we have provided to us these KSP values. So over here, we have I've calculated what we would have for a saturated solution. So if we have an equilibrium present where we have as much potassium and nitrate or iron and nitrate or lead and nitrate or iron and chloride dissolved for these different substances, and we see these values are fairly large concentrations that we would have. And we can connect that to the fact that these are smaller concentrations. So what we have present here are smaller than a saturated solution, and what that tells us that amount will be fully dissolved and it will be fully dissociated in those different solutions. So that gives something helpful for us to know when we're thinking about whether these are actually fully dissolved or only they're partially dissolved in our solution. Now then, with that information, we now know that means we have lead 2 plus and nitrate ions. We have potassium ions and nitrate ions. Here we have potassium ions and nitrate ions. Here we have iron 2 plus and nitrate ions that we'd have present in our solution. And the reason why we're addressing that, because all of these are going to contribute to the ionic strength of the solution that we have. And this is going to be important as we think about the activity of the relative ions as they're undergoing these reactions. Now that we have kind of that information, we want to address, well, now that we have these two cells, let's first figure out what kinds of reactions we're going to have. Which one's going to be reduced, which one's going to be oxidized? So we have over here our half reactions for our standard reduction potentials. And we notice that our lead is less negative in its standard reduction potential, meaning that it is a stronger reduction reaction. So that would be, gaining the electrons. And our iron, if we think about going the other way, if we were to write it as solid iron going to iron 2 plus and 2 electrons, that potential would be positive 0.440 now because it's gaining electrons, losing electrons. We flip the side of that, we flip the order of our reactants and products, and so that gives us positive 0.44. And this is a stronger oxidation reaction that we would see present here. So we have our reduction reactions, we have our oxidation reactions, and so then what that tells me, if I go down to kind of identifying what's happening here, for our oxidation side of our cell, we're going to have our solid iron going to produce iron 2 plus and then our 2 electrons. And our standard oxidation potential is 0.440 volts. And then we can go ahead and look at and compare that to our reduction side. And so we have our lead gaining our 2 electrons to give us our solid lead, and this standard reduction potential is negative 0.126 volts. So we have both of those pieces of information, but now what we want to do is identify what the cell potential would be based upon the fact that we're not at standard conditions. A, we're not at standard temperature. B, we're not at standard concentration. So let's correspond that to the Nernst equation for each of these. So if we go here for oxidation, we would see that our oxidation potential is going to be our standard oxidation potential, 0.440 volts, minus our 300 Kelvin. We have 2 electrons being transferred here, and then I'm going to leave F, just because our R and F are constants and we don't need to necessarily write them out. Natural log of Q, and we look at our Q here for this reaction that we have here. So we notice that I have iron as a product, so that would be the activity of our iron 2 plus divided by the reactants, when this case is a pure solid, so we could say 1, or effectively we could just say it's the activity of our iron 2 plus. Then we go ahead and we go to our reduction side, and so now we have our standard reduction potential, the negative 0.126 volts, minus, again, R, we're at 300 Kelvin. We have 2 electrons being transferred here, and then our value for the Faraday constant, natural log. And now we notice that for our products, we have no aqueous ions. We have nothing that's going to change in concentration. And then our reactants is our lead ions. And so then we'd have that divided by the activity of our lead ions. Now what we need to know for each of these, for example, the activity of our lead ions, we need to know the activity coefficient times the actual concentration of our lead ions. We also need to know, similarly, to find the activity of our iron ions, we need to know the activity coefficient of iron times the actual concentration of our iron ions. Now, in order for us to do that, hopefully what's ringing in our minds and thinking, I need to know the activity coefficient for these here, that tells me I need to know what the ionic strength is. If we don't know the ionic strength of our solution, we don't have the ability to identify that. So each of these are separate solutions, but what we notice is that they're very similar in what's present there. So we notice we have the same concentration, same molar ratios and how they distribute for these two, the iron and the lead nitrates. And then we also are starting with the same concentrations of our potassium nitrate. So what we'll see is that the ionic strength of both of these are the same, and that's simply because we're starting with the same relative concentrations between each of those. So let's go ahead and identify what the ionic strength of one of these would be, and we could use that for the other one as well. So the ionic strength of our first solution, maybe we can start with our lead 2 plus solution. It's going to be 1/2 times the concentration of all the ions present. So I'm going to go ahead and fill that in here. So this would give us an ionic strength of 0.033 molarity, including all of these different ions and the relative charges that they would have. Now what we could then use those to do is to find the activity coefficients of both of our ions present here. So the activity coefficient of iron 2 plus, we could also find the activity coefficient of lead 2 plus. Now again, I'm only making this the ability for us to say the ionic strength of both as the same for these two different solutions because they have the same ions and concentrations present. If they're different solutions, like our next example that we'll look at, then we have different ionic strengths for those different solutions. Okay, so we get an ionic strength of the activity coefficient of our iron ion, 0.534, the activity coefficient of our lead ion, 0.511. And so now we have the ability to go ahead, since we know our lead ion concentration, our activity coefficients for those different species, now we can go ahead and plug in the information that we know with regards to those. So let's go ahead and do that for our oxidation potential first. So our oxidation potential, 0.440 volts minus, I'm going to go ahead and calculate what all of those are together. And as we do that, we get 0.0129. And what's left out is units of volts times the natural log of our activity coefficient of our iron ion, which is going to be 0.534, and then the actual concentration of those iron ions are 1 times 10 to the negative third. And so that would give us our activity of those, and we go ahead and plug it in, and we get an oxidation potential of 0.537 volts. And we can go ahead and look at our other example here. We have our reduction is going to be negative 0.126 volts minus. Again, we're going to go ahead, plug in everything for all of this. So we're taking all of this, and we're going to calculate them with regards to the different species that we would have present here in our solution. 0.0129, and again, volts, natural log, 1 over the activity coefficient of our lead ions, 0.511, the actual concentration, 1 times 10 to the negative third, and so that's going to give us a reduction potential of negative 0.224 volts. So now we can go ahead and combine both of those here, and we know that we can take our overall cell potential is equal to what we identify as our oxidation potential. So we're going to get 0.537 volts for our oxidation potential, negative 0.224 volts for our reduction potential, and that's going to give us an overall cell potential of 0.313 volts. And so we think of what are some important ideas or concepts that we've thought about here as we're looking at these different steps here. One of them is activity and how that relates to ionic strength, so some reminders about that. KSP and solubility, specifically thinking about do we have a saturated solution or not, and how that may correspond to our equilibrium constant. And then thirdly, looking at the Nernst equation and our activity of whatever ions we have present in that redox reaction. So we have kind of those three ideas have been meshed together as we're considering the cell potential of these different species that we'd have present. So we combined all those different thoughts. These here were from when we originally talked about acids and bases and equilibrium and all these other equilibrium reactions. We talked about activity, and now we're kind of melding these together when we're thinking about our Nernst equation, the reactions that we would have here. So that was our first step in identifying what our cell potential would be. Now the second step is then thinking, well, we measured the cell potential for known concentrations. Can we use this information to identify something unknown? And so that's our second proposed idea here. We want to figure out a way for us to be able to identify the concentration of lead ions in a solution when we are going to compare that to our iron 2+ as a reference electrode. And what that means is we want to have a constant oxidation potential for that reference electrode. We do not want it to be varying with any other pieces that are going to influence that. And so then what we're going to do is we're going to think, okay, how can I make that a standard electrode? And what we can do is we can consider, we already know some information about our lead side. So if we just start with that, we know our reduction is going to be our standard reduction potential of lead, negative 0.126, minus our RT over NF. It's the same, so the 0.0129 volts. Again, this is RT over NF. We're just filling those numbers in with regards to the cells that we've already used. Temperatures we're at. Natural log of 1 over our lead. Concentration and our activity coefficient that we'd have here. So again, if these are unknown, then we can, if we knew something about our cell potential, that's going to tell us information about those lead concentrations. So that would be, this is going to be our variable that's going to be changing. So our reduction potential could be changing relative to the concentrations of the lead ions. However, when we're looking at our oxidation potentials, what we'll see here is that our oxidation potential, again, is our 0.440 minus our RT over NF, 0.0129 volts, natural log of the activity of our iron ions and the concentration of those. So we need this to remain constant. That means we need to have it where if this reaction proceeds and we produce more iron ions, those iron ions somehow come out of the solution. And the way that we can get these here to be fixed or constant, even if the reaction's occurring, is that what we can do is we can think about, well, what if we create a saturated solution containing Fe2+ as one of the ions of that solid that has been dissolved. Because then if we have that saturated solution, if we produce more iron, it's going to precipitate out because we are now in this equilibrium place with our solid that contains those iron 2+ ions. So that's what we need to figure out, is how can we actually fill that in and make a solution that is saturated. Well, I gave us information about two different iron-containing salts. One of them is iron nitrate, one of them is iron chloride. We can use either one of these and make a saturated solution containing these. Well, let's go ahead and choose, maybe let's look at iron nitrate, simply because that's what we've been looking at before with regards to our solutions. So if we have our iron nitrate here, it's going to go, if it's going to undergo this equilibrium KSP reaction, iron 2+, 2 nitrate ions that we'd have as part of this. And now we want to see here, we know our KSP is 18.9 for this specific solid. Well, if I think about it's going to be at equilibrium, I'm going to have as much dissolved as possible. I'm going to have a saturated solution. We go ahead and set up a Rice table, and we see here where we ignore our solid. We're not going to directly add in some of these other ions. So we're going to make some amount of them. And so we end up with X and 2X for our concentrations here. Now what we don't know is we don't know our ionic strength. We don't know the ionic strength of this solution. So what we're going to need to do is we're going to do a first approximation and say, what would the concentration be if our gamma value was 1, right? We're assuming our ionic strength is low, which is not going to be because we have high concentrations of these ions. So we're going to say if our activity coefficients are 1, that means our concentration, for example, of iron is equal to the activity of iron. And that's because we're saying our activity coefficient is 1. So we could take our KSP, which again is our activity of our iron, times the activity of the nitrate ion squared. And so we could take that 18.9 as equal to X times 2X squared. We go ahead and solve for that concentration that we would get, and we would get 1.68 molarity for our iron ions, and our nitrate ions would be double that. Well, once we have that, we can then go ahead and say, and I'm not going to show all the details of how we calculate this. I think we're comfortable calculating our ionic strength. We would find our ionic strength is 5.04 molarity from these concentrations of nitrate, 3. So double this concentration, and then here we have our iron is the 1.68. So we have these different concentrations giving us this ionic strength. Well, that's going to give us an activity coefficient of our iron, 0.144, and activity coefficient of the nitrate ion of 0.441. So now what we do is we now have a better value for our activity coefficient than 1. we go ahead and we replug this in thinking about our activity coefficients here. We have our 18.9 equals the activity coefficient, 0.144 of iron, times its actual concentration, times the activity coefficient of nitrate, 0.441, times its concentration, 2x, and then we square that whole thing, because remember our activity is squared. We go ahead and we resolve for our x value, and we get now a concentration of 5.52 molarity. So we notice that first approximation not so great, and that's because we ignored the fact that this is a very high ionic strength solution. And so then from there, now we go ahead and we recalculate our activity coefficients. So we get an iron 2 plus activity coefficient of 0.121 and a nitrate coefficient of 0.387. So now we have a couple pieces of information that are important. We have our actual concentration of the iron 2 plus. We have the activity coefficient of our iron, which is going to be included up here to calculate our fixed value. And so then now we have this kind of fixed scenario for our oxidation potential. So let's go ahead and calculate that. So once we do this, we're going to get this kind of standard fixed oxidation potential of 0.445 volts for our oxidation potential. And so now our overall cell potential is only going to be changing or varying based upon our lead concentration. And that's what we're going to look at in our next step. So our next step, we're going to say, well, we have this fixed value. We know our overall cell potential is our oxidation potential plus our reduction potential. So we can go ahead and fill in the information that we have there, 0.445 volts for our oxidation potential. Our reduction potential, negative 0.126 volts minus the RT or NF, so what we already expressed up here in our reduction potential. So 0.0129 volts times the natural log of 1 over activity coefficient of our lead ions, the actual concentrations of our lead ions. And so now we have an expression for this. We can simplify this by combining kind of our known values. And we would end up getting, when we combine those, 0.319 volts minus the 0.0129 times the natural log of the inverse of our activity coefficient of our lead ions times the lead ion concentration. So now we have this expression. If we measure our cell potential, we can quantify it, and we knew our ionic strength, we could quantify the concentration of our lead ions. Well, in this instance, we're thinking, this would be like a calibration scenario. If we made a solution that we know the concentration of our lead ions, let's see what our cell potential would be. So we're going to go ahead and plug in the information we get there. Now, from our ionic strength, we have the ability to calculate the activity coefficient of lead 2 plus, which is 0.376 from that ionic strength and its charge that we would have. And so now we have all the information we need to calculate our cell potential, 0.319 volts minus 0.0129 times the natural log of 1 over 0.376, 1.8 times 10 to the negative 3, and we would get a cell potential of 0.225 volts. Now again, the instance would be if we were given, maybe we measure the cell potential and we get a potential for this value, this substance of 0.318, that's going to tell us something about the concentration of our lead 2 plus ions. So this is getting us kind of exposed to the connection between activity, concentration, cell potential of our half reactions, and we're going to continue to unpack this as we go further in our coursework here and thinking about how our activity relates back to these specific redox reactions.